Hi, thanks for joining me. Today I'm going to be going over problem 1, part 2 from week 4 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find out more details about the competition, and I'll also leave a link to my solution to part 1 as well. Anyway, a quick disclosure before I get into this problem. It was kind of ambiguous how the problem was initially stated. There were a few different ways to interpret it, and in fact the way that I think it was intended to be interpreted, that problem I'm not going to be going over in this video, simply because the solution to that is actually quite long and quite technical, and it's not very elegant either. But another way you could interpret the problem, which is what I'm going to show you now, that the problem, how I kind of initially interpreted it, and the solution is a lot more sort of videoable. It's a lot nicer to make a video for because it's a little bit shorter and a lot more elegant. Anyway, this is the problem I'm going to be going over in this video, and I've only written it kind of in short, in bullet points, but I'll leave how I've interpreted the problem in full in the description below if you want to have a full read of the problem. But anyway, let me quickly read it, I'll give you a chance to have a go at the problem, and then I'll get stuck into a solution. Anyway, we have n lily pads like we did in part 1, and n is a positive integer at least 2, and we also have n frogs labelled 1, 2, 3 all the way up to n, and initially each frog is on its own lily pad, so n lily pads, n frogs, each frog is on its own lily pad by itself. Okay, now only some pairs of lily pads are close enough together to be jumped between, forming a tree graph. So you may have seen that there's a little graph up here, and now what these vertices here represent are the lily pads, and the lily pads, only some of them are close enough so that you can jump from one lily pad to the other, and we kind of have these edges here representing when you can jump between lily pads. So for example, these two lily pads, because there's an edge between them, you can jump between them. However, this lily pad and say this lily pad, there's no direct edge between those two, hence you can't jump from that lily pad to that lily pad. So only some pairs of lily pads are close enough to be jumped between, and it forms a tree graph. So a tree graph is simply a graph theory graph where you've got it's all connected and there are no cycles, as we have here. Okay, and of course this is just like a particular example just to illustrate what's going on in this bullet point here. Anyway, each second only one frog jumps, kind of governed by this rule here. So on the tth second, frog t mod n jumps to the lily pad closest to frog t plus 1 mod n. Okay, so let me quickly digest this give you a chance to digest this bullet point. Let me break it down. So on the tth second, so suppose t is 3, so on the third second, frog 3 mod n, so that would probably be frog 3 if n is bigger than 3. Anyway, frog 3 will jump to the lily pad closest to frog 4. Okay, now by closest I mean, well, the fact that we have a tree graph here means that there is a unique path between frog 3 and frog 4. So if frog 3 is say on this lily pad and frog 4 is say on this lily pad, there is a unique path from frog 3 to frog 4 on the vertices on that graph there, and that's just a property of tree graphs. And so if this was frog 3 and this is frog 4, then the unique path would be this guy there. So when we say that frog 3 moves to the lily pad closest to frog 4, we just mean the one which is kind of on this path here. So frog 3 would move to this lily pad here like so. So hopefully that all makes sense. And this mod n stuff, so this mod n here is so that after the nth second we'll have an n plus 1th second, but that's when the first frog jump. So we kind of loop back. So once the nth frog has jumped, and the nth frog will be chasing frog n plus 1 mod n, which is just frog 1. So frog n will be chasing frog 1. So once frog n has jumped after n seconds, then on the n plus 1th second, or n plus 1st second, I'm not sure, frog 1 will then jump chasing frog 2. Then on the n plus 2nd second, frog 2 will be chasing frog 3, and so on. So hopefully that all makes sense, but essentially it's just this mod n stuff is just so we know that we're looping back around after n seconds. We're not just stopping after n seconds. Anyway, what our problem is, we want to find all tree graphs such that no matter what the initial placement of frogs is, all frogs will end up on the same lily pad. Now remember, as I said before, this is kind of one interpretation of how the problem was initially written, and there are a couple of other ways, or at least one other way you could have interpreted the problem, but this is the one I'm going to be using for this video, and that's the solution I'm about to provide. But if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first thing we're going to do is introduce a definition, and that is we're going to define a minute to just be n seconds like so, because of course everything we're doing is working in n seconds, so this kind of makes sense. The next thing we're going to do is state and prove a lemma, this guy here, and it's kind of split into two parts, but let me read it out in full and then I'll kind of break down each part. If after t minutes, frog1 and frog_n are on the same lily pad, then frog1 and frog_n will be on the same lily pad at the end of each minute thereafter, and frogs 1 through n-1 will chase like they did in part 1. So the first part of the lemma is kind of this bit here, up until the and, oopsie daisy, like so. So if frog1 and frog_n are on the same lily pad after some t minutes, so at the end of a tth minute, frog1 and frog_n are on the same lily pad, then I claim for all, I claim that for at the end of any minute after t minutes, so at the end of the t plus 1th minute, at the end of the t plus 2th minute, and so on, frog1 and frog_n are going to be on the same lily pad. So that's the first part of the lemma. And the second part says that, where are we looking? Here, frogs 1 through n-1 will chase like they did in part 1. So what I mean by that is in part 1, all the frogs jumped at the same time, whereas in part 2, the one we're solving today, is the one we have all the frogs jumping on their own second. So frog 1 will jump by itself on the first second, then frog 2 will jump by itself on the second, and so on. However, in part 1, we had all frogs jumping instantaneously on the same second. Okay, but I claim that we can kind of treat the problem like we did in part 1. In other words, at the end of, if after t minutes frog1 and frog_n are on the same lily pad, thereafter what we can do is just essentially model the t plus 1th minute as we did in part 1, at least for frogs 1 through n-1. Okay, now let's get into proving this lemma. Okay, so proving the first part of the lemma is actually not too difficult. So you want to prove that if frog1 and frog_n are on the same lily pad at the end of the tth minute, then they're going to be on the same lily pad at the end of all subsequent minutes. So let's just suppose they're on the same lily pad, say this guy here. So 1 and n are on that lily pad there. Then this is the end of the tth minute. So now let's start the t plus 1th minute, and frog1 will chase frog2. So there are one of two things that can happen. Either frog2 is on this lily pad, in which case frog1 doesn't move. So suppose that is the case. So suppose frog2 is also on this lily pad, then frog1 won't move. So frog1 will stay there. And then frog2 will chase frog3 wherever frog3 is. Frog3 will chase frog4 and so on. Then frog n-1 will chase frog n. But then frog n will chase frog 1. But because 1 hasn't moved, n won't move either because 1 is on the same lily pad as n. And hence we're going to have at the end of the t plus 1th minute, n and 1 are both on the same lily pad. Now the other case is if 2 is not on this lily pad, let's say 2 is here, then of course frog 1 is going to chase frog 2, so frog 1 is going to jump to this lily pad here, because of course that's the unique path between 1 and 2. So we get that. And then frog 2 will chase frog 3 will chase frog 4, and so on. Frog n-1 will chase frog n. Then it's n's turn to chase frog 1. But of course 1's only kind of moved one jump, so n can chase it and land on frog 1. So n will jump, and then frog 1 and frog n will end up on the same lily pad here. So that means at the end of the t plus 1th minute, they're on the same lily pad. And then you can kind of prove the rest by induction because they're on the same lily pad here. That means after the t plus 2th minute, using the exact same argument we had, they're also going to be on the same lily pad, and so on. So that proves the first part of the lemma. Let me clean this up, and then we'll prove the second part of our lemma. Okay, so what we want to do for part 2 is essentially prove that if we have frogs 1 through n-1 jumping, it's the same as if we had them all jumping at the same time, so how we would have done in part 1. And now how I'm going to prove this is kind of just illustrate it with an example, but hopefully you'll understand essentially why it holds. So I've drawn two copies of the same graph, and this is a case, I guess, n equals 5, and I put 1 and 5 on the same lily pad like so, and 4, 3, 2 like so, and of course we'll have a blank lily pad because there are 2 on the same one. Now what we would have in part 1 is that all the frogs jump at the same time. So frog 1 will be chasing frog 2, so because 1 is here and 2 is there, frog 1 would jump to this vertex here. So this is frog 1 jumping. Frog 2 would chase frog 3, so frog 2 would jump to that vertex there. Frog 3 would be chasing frog 4, so that's the unique path, so frog 3 would jump to that vertex there. And then frog 4 would be chasing frog 5, so frog 4 would jump to that vertex there. And we don't actually care about what frog 5 does because we're only considering up to n-1. So if this was part 1, our graph would now look something like this, with frog 1 here, let me make this bigger, 1 here and 2 here. 3 would now be on this vertex here, and 4 would also be on this vertex here, and 5 would be somewhere. We don't really care about where 5 is, but this would be the case. This is what we'd end up with frogs 1 through n minus 1, so 1 through 4 in this case. But now if we do it in part 2, where each frog jumps on its own second, well, frog 1 will chase frog 2, so frog 1 will jump to this vertex here, so it will get rid of it from there and put it there. It's quite difficult to see, let me just write it here, 3, 1. Frog 2 will chase frog 3, so frog 2 will join frog 1 and frog 3 on this lily pad here, like so. So this will become 3, 1, 2 on that lily pad. Then frog 3 will chase frog 4, so frog 3 will jump to this lily pad here with 5. And then frog 4 will jump up to this lily pad here because it's chasing frog 5. So frog 4 will jump here, and this will be 3, 4, 5. And now remember, we don't really care about where 5 is, but notice apart from that, everything else is the same because we've got 3 and 4 on this vertex here, and 1 and 2 on this vertex here. So this kind of illustrates what's going on in the second bar here, and hopefully if you ever think about it, you can see why it holds in general. But I'm going to consider this lemma proven. Let me clean up the whiteboard, and I'll continue. Okay, so now suppose that n is at least 3, and I claim that on any tree graph with n vertices, we can always find an initial arrangement of these frogs so that they'll never all be on the same lily pad. How I'm going to prove this is, well, I'm just going to kind of essentially provide you with an arrangement. Well, because n is at least 3 and we're looking at tree graphs, you can always find a vertex with degree at least 2. So there'll be a vertex with degree at least 2. So it will look something like this, but it could have other vertices coming out of it, but we're essentially only focused on these 3 vertices here. And what we're going to do is place frog 1 on this vertex here, frog 2 on this vertex here, and frog n on this vertex here. So this is kind of our initial arrangement, and I notice that this is fine because n is at least 3, so n is distinct from these two. And then of course if n is strictly bigger than 3, there'll be some other frogs that we have to consider as well, but we can just place them wherever we want. So whatever our tree graph looks like, doesn't really matter, we don't know what it looks like, but we'd place the remaining frogs on these lily pads like so. But we're only interested in these 3 here. Now, what I'm going to do is exploit the lemma that I just kind of stated and proved. First thing, notice that with this initial arrangement, frog 1 is going to start off in the first second by chasing frog 2, so it's going to jump onto that lily pad there. Now frog 2 is going to chase frog 3 wherever that is, it doesn't really matter, but then frog 3 will chase frog 4 and so on. Frog n minus 1 will chase frog n, and then frog n will chase frog 1, but because 1 is on this lily pad now, frog n will join it. So then after the first minute, frog 1 and frog n are on the same lily pad, and that means we can apply the lemma we just had. So after the first minute, frog 1 and frog n are on the same lily pad, so we know that thereafter frog 1 and frog n are going to be on the same lily pad at the end of each minute. So frog 1 and frog n will be on the same lily pad at the end of the second minute, the third minute, the fourth minute, and so on. And now what we're going to do is use the second part of the lemma, which says that frogs 1 through n minus 1 will act as if they did in part 1. Now remember, in part 1 what we did is we coloured the vertices using this kind of alternate colouring scheme. So some were blue and some were green, so that no adjacent vertices shared the same colour. So if we started off with this one blue, then we'd turn this one green, this one would be blue, these would turn green, and this one there would turn blue. So this alternate colouring scheme. And what we're going to do is do a very similar thing here, and essentially use the exact same argument, but now with just frogs 1 through n minus 1, to show that they can never all be on the same vertex. So let's suppose we use this example here, and let's kind of suppose that frog 3 was there in our initial kind of placement of the frogs. So then after the first minute, what we'd have is, let me redraw our graph. It would look something like this. Now frog 1 we showed goes onto this middle vertex. Frog 2 will chase frog 3, so frog 2 will go there. Frog 3 will will have to jump up there somewhere. And then frog 4 will do something, frog 5 will do something, and so on. And frog n, we know, jumps onto this vertex here, so let me just get rid of the 3, that's not important, and put n there. But what's important is that 1 and n are on the same vertex, but they're on a different coloured vertex to 2. Because we know that 2 must jump in the first minute. It must jump because we know how we initially placed the frogs was so that each frog was on a different lily pad, or each frog was on its own lily pad. So we know that 2 and 3 are on different lily pads, so in particular that means that 2 can't stay on the same lily pad, so it must move, and because all of its neighbours are of a different colour, we know that 2 will be on a different colour to how it initially was, and that's the vertex that frog1 and frog_n are on. So if this one here is, say, red, sorry, not red, if this one here was blue, then this one here is green. And of course, it doesn't really matter what, that can be green, this could be blue, it doesn't matter. But this one, say, is blue, and this one here is green. But by the second part of our lemma, we know that from here on, frogs 1 through n-1 will kind of act like they did in part 1, in which case we know, using a very similar argument, that there's always going to be at least one frog on blue and at least one frog on green. So if that doesn't make sense to you, you probably didn't see my part 1 video, so I'll leave a link to that in the description. Go and check that out. But essentially, using the exact same argument we did in part 1, from this situation, we can prove that there's always going to be one frog on blue, at least one frog on blue, and at least one frog on green, and hence all the frogs can never be on the same vertex. So that says that if n is bigger than or equal to 3, we can find an arrangement of frogs so that they're never on, so that they'll never all be on the same vertex. So to solve our problem, the final thing we have to do is just consider the case n equals 2, which is actually really straightforward. Let me clean up the whiteboard, and I'll do that case. Okay, so we have n equals 2, so we have two vertices, this guy and this guy, and our graph must be connected, so there must be an edge from this vertex to this vertex, and in fact this is the only graph on two vertices that's connected, and of course it is a tree as well. Now of course our initial placement must have frogs 1 and 2 on different vertices, so we could have 1 here and 2 here, or the other way around, but obviously it doesn't really matter. And now in the first second, frog 1 is going to jump and chase frog 2, so frog 1 will end up here, and then frog 1 and frog 2 are on the same vertex, so they're just going to stay there forever. And so this obviously does work. So this is a graph for which any arrangement of frogs initially placed on it will always end up in all the frogs ending up on the same lily pad at some point in the future, namely just after 1 second. So that solves our problem. There's only one graph that works for our problem. There's only one graph such that no matter how you initially place the frogs on that graph, they'll always end up on the same vertex, and that graph is this guy here, just the n equals 2, the graph that looks like this. I hope my explanation has made sense, and I apologize that the initial problem was kind of poorly written, or perhaps kind of ambiguous, but I hope this solution has all made sense to the problem that I answered. Thank you for watching, and as I said, part 1 is in the description below if you haven't checked it out already. Thanks for watching, I'll catch you in the next one. Have a great day.